Good afternoon. My name is Sonia from TechnologyCatalogue.com, and I would like to welcome you to our new webinar about biomonitoring. Before leaving you with Harry Pullman from H2O Technologies, I will briefly introduce Technology Catalog. At Technology Catalog, we want to make finding technology in the energy industry very easy and immediate, together with all required support to deploy these technologies. Indeed, there is a current problem. There is a very wide range of available solutions which can cause confusion about what are the best of them and the best investment for your business. So I would like to invite you to find out more and to visit our website to find and compare these new technologies that will so enhance your business. And also, last but not least, it's a great opportunity to be introduced to new technologies without having to travel. I will now let the stage to Harry, who will give you some valuable insights on the biological risks in the intake and cooling water systems. Just to provide you with some information, the webinar will last around 20 minutes. And at the end, we're going to have 10 minutes time for questions and answers. So if you have any, please use the chat on your right. And at the end of the webinar, there is going to be a surprise for you. So it's a case study provided by H2O Solutions. And I hope you enjoy.
Thank you very much, Sonia, for this introduction. My name is Harry Pullman. I'm heading the company H2O Biofouling Solutions. We are based in the Netherlands, but we work globally. And the main objective of our company is to predict, prevent, and control biofouling in water systems. The webinar of today will cover items around biomonitoring. We talk a little bit about the intake and cooling water systems, how biofouling is settling, what is the actual impact of biofouling on a utility and a plant, the biofouling monitoring options, both for macrofouling and microfouling, the benefits of biofouling monitoring, and at the end there is a space for questions and answers. The questions best to be provided through the chat function. Utilities that use surface water not only extract water from like a river or a sea, but with the water also biology. A part of the animals, they settle and grow in your cooling water and piping system. Now, the reasons why these animals grow in these systems is because these systems are actually designed and provide optimal conditions for these species. Like there is a continuous flow of water which provide the animals nutrients and oxygen. So they have the opportunity to settle and to grow and to feed continuously. The water velocities in a cooling water intake, cooling water system are generally between 0.2 and 2 meters per second. This is favorable for most of the biofouling species to settle and grow. There is turbulence in part of the systems in respect, for example, in bands, which is favorable for some species like mussels. They prefer these kind of areas in a system. There is no light, or at least dimmed, which is also preferable for most biofouling species to settle and grow. There are no predators. Due to the screening at the inlet of a intake system, you keep most of the predators, like ducks, away from your cooling water system. So the animals, they have like a very safe environment to settle and grow. In cooling towers, the temperatures are relatively high and provide an excellent condition for bacteria to settle and to grow into a biofilm. How fast does biofouling happen? Now, first you see that when you have a clean pipe and you expose it to water, surface water, within a few minutes an organic film layer will occur. Once this film layer is present, there is a habitat where bacteria will settle and grow. That happens within 1 day. After a week, different animals like protozoa will start to colonize in the layer of bacteria, which will form a biofilm. After 2-3 weeks, this layer is an optimal habitat for larvae of tertiary colonizers like mussels, oysters, barnacles to settle and grow. So you see that if you have a clean pipe and you expose it to water, it will take you maximum 3 weeks before there is an opportunity for mussels, oysters, barnacle larvae to settle and grow. So a fouling of a pipe can go pretty fast. Generally, there are 2 types of biofouling species. Microfouling, that's bacteria which form a bacterial slime layer, which is called a biofilm. This type of fouling happens in all 3 different kinds of cooling water systems, like a one-stroke cooling water system, an open recirculation system with a cooling tower, or a closed loop water system. In cooling towers, there is an additional risk where the slime layers can foul the packages of the cooling tower. Macrofouling species like mussels, oysters, barnacles, they settle and grow generally and form problems in one-stroke cooling water systems and also in the inlet part of a open recirculation system. Now, the impact of biofouling can be pretty severe. We are aware and we've been confronted with plants that had an unexpected outage, shutdown, caused by biofouling. Biofouling can result in operational risks on the operational reliability. It can cause head loss. So if you have shell growth in an intake pipe, it increases the wall roughness of the intake pipe, which will result in head loss in the intake basin where the cooling water pumps are located. Head loss can arrive pretty fast, even when you have a small layer of fouling of mussel organisms settling in the pipe. So visually it doesn't look bad, but it already can have a very significant impact on head loss, which can trip a plant due to the low levels of water. The heat exchanger efficiency will be reduced. A slime layer caused by a biofilm will have a high impact on the heat transfer rate. Biofilms can cause corrosion, microbial-induced corrosion, due to the fact that underneath the biofilm layer, typical type of bacteria can grow, which cause MIC. In addition, in cooling towers, biofilms, they form a perfect habitat for organisms which can be the host of Legionella bacteria, and once released in the water and in the water spray, the Legionella bacteria can be released and cause a health problem for the people in the surroundings of a cooling tower. Now, biofouling always results in higher operation and maintenance costs due to the damage or due to the fact it's a foul system. The impact can go up to more than 1 million euros per day in a circumstance where there is an unplanned shutdown of the plant. An example of the impact of a biofilm on the heat transfer rate at a heat exchanger. A biofilm of 0.12 millimeter will already result in an increase or a decrease more or less in heat transfer efficiency of 1 Kelvin. So it has a high impact on the energy which is required to cool the processes. As mentioned, the biofilm layer is a perfect habitat for MIC bacteria like sulfur-reducing bacteria, but also the Legionella bacteria. Besides operational impact, biofilm also results in an environmental impact. When a foul system is present, you need more and higher concentrations of chemicals to actually mitigate and prevent further growth of biofouling. So there's higher demand of chemical dosing. Higher chemical dosing results in a higher discharge of biocides or the byproducts of these biocides. For example, bromoform as a byproduct from hypochlorite. When you get corrosion due to MIC bacteria, generally there's a spill of process fluid into the cooling water, which is discharged at the outlet. Head loss requires a higher pump capacity to get sufficient water into the intake basin to feed the condensers and the heat exchangers. Higher pump capacity needs and results in higher carbon dioxide emissions, which can be thousands of tons per year, only caused by head loss. So why do you want to apply a biomonitoring tool? Now, generally that's because if you do chemical monitoring, for example, measure the concentration of the biocide you use, or depend on process data like head loss or head levels in the intake basin, or a K value for the heat transfer rate, generally that's not provides a full insight in the real attachment and growth of biofouling. So a biofouling monitoring to get insight in the biofouling settlement risk will provide additional benefits for the operators. In addition, it provides also opportunities to adjust the biofouling treatment to see the efficiency and of the changes of the applied chemical dosing. So already at a very early stage, you can prevent operational and health problems caused by biofouling by adjusting your biofouling control procedure based on the feedback received from the monitoring. Now, for macrofouling monitoring, you can use a monitor which is shown in these pictures. And this monitor we developed provides real-time insight in macrofouling settlement and growth rates of all different kinds of macrofouling species. It also provides insight in the breeding periods. So macrofouling is not available throughout the whole year. Depending on the location and depending on the species, you got specific breeding periods where the animals release larvae, which enter a cooling water system and which can settle in a cooling water system itself. So you can use the monitor to tailor your dosing period throughout the year based on breeding periods and availability of larvae. It also detects new invasive species. So if there is a new invasive species arriving in the area of your utility, if it starts to enter the cooling water system, this monitor will give you an early warning, which gives you the opportunity to adjust your chemical treatment and dosing to make sure that it doesn't foul your system if the species prove to be more resistant than the existing ones for your chemical dosing. It's an early warning for potential risks to plant reliability, more or less. Now, the design of our monitor, which is called the BioVision monitor, what we try to do is to mimic the conditions inside an intake and cooling water system. So we have a monitor where 5 fouling coupons are installed, and along the coupons there is a range of velocities, water velocities of 0.2 to 2 meters per second, which mimics more or less the general range of velocities in an intake and cooling water system. In addition, there is turbulence in the monitor, which is favorable for specific species like mussels. We tried to make the monitor easy to install and operate, so to make it a very easy tool for operators. No power is required, so it's very easy to install in an industrial plant. The monitoring is done by a visual check, and the monitor has been applied now for many, many years at all different types of industries, like power plants, oil and gas installations, desalination plants, chemical and heavy industries. The options to monitor is where do you put the monitor in a system? That's more or less always the question. Now, generally, we advise to put a monitor in front of the furthest heat exchanger or condenser to have the longest residence time within a cooling water system. But also you can install the monitor at a location where there is a known and historic fouling problem to get insight at that specific location. Now, optional, you can install a second monitor as a control. So at a spot where there is no chemical dosing to have a comparison on efficiency. This monitor, as mentioned, measures settlement period, the type of the fouling rate. In addition, you can measure the mortality rate. So when you have a foul system and plates or the coupons are fouled with organisms, you adjust your dosing regime, and you can see the effect also on the coupons of the monitor. As mentioned, monitoring will be done visually. In general, the monitors are provided as a service contract. We inspect them, or we train operators to inspect them visually, take photographic images, and we will identify the species, the growth rate, the size of the species, to follow more or less the biofouling risks throughout the seasons. Optional, there's an opportunity to analyze the larvae settlement using a microscope on these coupons. The monitoring results and the monitor will provide insight into the effectiveness of the biofouling control procedure, settlement and growth rate of the biofouling species, seasonal risks of biofouling settlement, and insight in the effect of any adjustment done on the biofouling control procedure. More or less, if you install this monitor, there is no more unexpected operational issue due to biofouling, since you have an early warning. Now, this slide is referring to the case study which will be handed out after the webinar. It's about the Uniper Maasvlakte power plant, where we installed these monitors since 2014. Now, the results we get every 14 days with a check. At Maasvlakte, we also do a inspection of the cooling water system once there is a plant outage. And based on the results we get from the inspection, that's like a very good comparison to the results we found using the biomonitors. So that was proven that the biomonitors will actually provide a very reliable one-on-one image of the actual situation in a cooling water system. To monitor the other type of biofouling, microfouling, bacteria, traditionally they are measured in water phase. Usually most of the analyses present are done in the water phase of a system, while bacteria in a biofilm cause a real problem, like MIC or Legionella. So you need to look at the biofilm and monitor the biofilm. That can be done offline through microbiology analysis, which generally takes time and is costly, but you can also do it online using a biofilm probe monitoring system. The biofilm probe is an online monitoring system which provides the opportunity to get an early warning on a biofilm buildup. It also provides insight in mitigation activities. So if you change the dosing regime, what will be the effect on the actual biofilm? And can you reduce the biofilm? It provides real-time feedback, and it's a pretty easy and proven technology to use. Now, the measurement principle is there are two electrodes in the probe, consisting of a series of discs. One electrode set is polarized every hour, of 1 hour per day. That provides an applied current signal, and the other electrode more or less measures continuously the resistance between the electrodes. That's a generated current you measure. The applied current tells you something about the thickness of the biofilm. The generated current provides you information on the activity of the biofilm. So when the signal is changing from baseline, there is a signal of microbial settlement, as you see in the graph, and the probe can provide an alarm function, and which will change the signal into a different color, red, as seen in the graph. So when there is a red signal, you know there is a biofilm present in your cooling water system. Now, we applied this system at different locations, and this is an example of a graph we created at the power plant in the Netherlands with an open recirculating cooling system. So we measured in the cooling tower basin, And originally the plant applied a 75-minute dosing per day with hypochlorite with a level of 0.6 milligram per liter total residual oxidant. By using this probe, we got a signal of biofilm buildup. So the 75 minutes per day were sufficient to prevent the biofilm buildup. So we stopped the dosing and we increased the biofilm on the probe. And then we start to dose different time intervals. And after some examples, we noted that a 30-minute dosing per week for this location was already sufficient to prevent biofilm buildup. So instead of dosing 75 minutes per day, we switched to 30 minutes per week. We were able to control biofilm buildup in this specific cooling tower. That obviously resulted in a high cost benefit, but also an environmental benefit because you're not dosing as much chemical to your water and discharging it. Now, biofouling monitoring obviously provides real-time insight in the risks for biofouling settlement and growth, both for macrofouling and microfouling biofilms. It provides online feedback on the biofouling status using proven technologies. Both technologies shown in this presentation are applied for many years at all different kinds of industries at different places in the world. The tools will help to increase biocide dosing effectiveness at a very early stage before problems arise. So you got the opportunity that whenever there's a problem arising, so you get settlement, you can already start mitigating it at a very early stage. Now, the benefits of biomonitoring, this is the last slide of my presentation. It provides a guarantee on plant availability. So there is no unexpected outage, there is no risk for head loss, which result in an outage. Production capacity guarantee. So you can be guaranteed that your desalination plant will produce water according to your contract. You can be guaranteed you can produce power according the specification of the power plant. So there is no risk for biofouling in that area. It improves operational reliability because you don't have the risk for MIC. You can already mitigate it at a very early stage before MIC actually starts to arise. OPEX saving, reduction of chemical cost because you can optimize your chemical dosing. That obviously results in a less environmental impact to water and air. And last but not least, prevent human health risk caused by Legionella. Thank you very much. I'd like to give the floor again to Sonia to move to the Q&A session.
Thank you so much, Harry. It was a very interesting session. Before starting the Q&A session, I would like to share with you the case study. It's going to be available now. If any of you has some question, please just type your comment in the chat box. I will be happy to answer. I may ask you something in the meantime. So do you only change dosing time or dosage levels, but also location? And can this testing be done by operator personnel, for example, on offshore?
Yes. To answer your last question, yes. Generally, when we install these monitoring systems, we train operators to apply the monitoring themselves. So we will guide them more or less from a distance. The location for monitoring, that depends a little bit on the system, but usually at a critical spot in the system. So for example, in a power plant, at an inlet of the condenser. For a desalination plant, generally just before the first filtration step of the seawater.
Okay, we got a question. Do you have any experiences with online bacteria monitoring?
Yes, we do. We are testing, we are continuously testing and looking for new technologies which will add value more or less to the monitoring technologies we already apply. And we are testing at the moment also a system with an online bacterial monitoring, which is a bacterial monitoring in the water phase, and try to compare it with the monitoring tools we use for biofilms. And I must say that we get very interesting results in that respect. And there will be, through our website, through our channels on LinkedIn, there will be updates and on results, more or less, on these kind of projects.
Right. Then, did you test the effect of different chemicals or biocides? What is the most effective chemical?
Yeah, we test different chemicals. We test different chemicals because our clients not use the same chemical all over the world. So in that respect, we use different chemicals. In addition, we do pilots and tests, and recently we are doing some testing with testing different chemicals on the mitigation effect on biofilms. So in those respect, we test different chemicals. To answer the question, what is the best chemical to use? That's difficult because that depends on the species you try to mitigate and on the cooling water system layout. So for one screw or an open recirculation system, generally different type of chemicals would be more beneficial to use and more effective. In addition, you depend on the used based on the limitations provided by water authorities in a permit.
Couple of other questions. Any benefit from changing the time of dosing?
Yes, but that depends a little bit on the type of system. But the time of dosing, obviously you can change your dosing time in two different ways. If you look at intake systems, you can tailor more or less your dosing and tune it based on a seasonal effect. So when there are larvae available in the surface water, then you start your dosing. If there are no larvae of macrofouling species in the surface water, then it's of no use to dose any chemicals to try to mitigate them. In addition, if you change the dosing times during a day, for example, if you have like an intermittent or a shock dosing, the dosing times can also be tuned based on the buildup of biofouling. So using the biofouling monitoring systems, you get a tool more or less to tune also the dosing times.
Couple of other questions. You're a very popular guy, Harry. So
I'm happy to see so.
What is the typical level of free chlorine in discharged cooling water?
Now that depends. If you look at a one-stroke cooling water system, obviously the typical level of free chlorine in a discharge level is just within the limit of the water authorities. And a discharge permit gives you the freedom, more or less, and the opportunity to optimize your chlorine dosing up to the heat exchanger or the condenser itself. And depending on the limitation, you can use a level of chlorine. Now, what is typically the level of free chlorine at discharge? In the Netherlands, it depends a little bit on the location, but it's between 1.1 and 0.2 milligrams per liter. For example, in Qatar, it's 0.05. But also I know countries in the Gulf region which it's 0.5, so 10 times higher than the neighbor country. So it really depends on the country and the water authorities what values is set.
Okay, then are the units affected by inorganic deposits such as iron or manganese in drinking water system?
If that question is more or less related to desalination plants, then no. The units, I'm just trying to understand the question a little bit more in detail. The units we are not talking about the monitoring units or the unit of the utility itself. But the monitoring systems itself are not interfered with these components. And obviously, biofouling can result in the release of certain components, metal components, also in higher concentration than produced water. I mean, I'm aware of a location where like an MED desalination plant resulted in higher copper levels in the produced water.
Then the last question for this session, because we're running out of time, is it possible to use the biomonitoring macrofouling, especially not only for warning, but also for quantification?
Yes, that's possible. Because you're not only looking at the when they arrive, but also how many, and also the growth rate. So you can also use it for quantification purposes.
Okay. Well, the time we have available is over, unfortunately. Before letting you go, I would like to remind you that in the next few days, we are going to receive the replay video, the case study, and also the slides, in case you joined a bit later. And I would also invite you to visit our website, TechnologyCatalogue.com, to have a full overview of course, our technology offer. And thank you, Harry, for being with us today. And I hope you all enjoyed this session.
Thank you very much. And thank you all for joining this webinar.
Thank you so much. Have a nice day.
Bye-bye.